Imagine spacecraft, launched decades ago, drifting silently through the cosmic abyss, thousands of light years from Earth. Now, imagine those same spacecraft, defying the very laws of physics we thought we understood, slowing down for no apparent reason. What if I told you that for over 30 years, two of humanity's most ambitious probes experienced an unexplained force, pulling them back towards the Sun? A force that baffled the brightest minds at NASA, hinting at a hidden physics at the very edge of our solar system. The Pioneer Anomaly wasn't just a glitch, it was a cosmic whisper begging us to rethink everything. To truly grasp the perplexing nature of the Pioneer Anomaly, we need to journey back to the early 1970s, a golden age of space exploration. NASA, fresh from the lunar triumphs of Apollo, set its sights on the outer solar system. Enter Pioneer 10 and Pioneer 11. These weren't your everyday satellites. These were trailblazers, designed to be the first human-made objects to ever cross the asteroid belt, photograph Jupiter, and then venture beyond the known planetary boundaries into the vast, cold emptiness of interstellar space. Pioneer 10 launched in 1972, followed by Pioneer 11 in 1973. Each carried a golden plaque, a message in a bottle for any intelligent life that might one day intercept them, depicting human figures and the origin of their journey. Their mission was audacious, their technology cutting edge for the era, and their success would etch their names into the annals of exploration. For years, they performed flawlessly, sending back breathtaking images of Jupiter's swirling storms and Saturn's majestic rings. They were heroes, quietly pushing the boundaries of human knowledge with every passing mile. But as they sailed further and further away from the Sun, past the orbits of Saturn and Uranus, a subtle, disturbing pattern began to emerge in the data. Tiny, almost imperceptible at first, it was a persistent deceleration, a gentle tug pulling them back, much like an invisible hand. This was not predicted. This was not planned. And it would soon become one of the most enduring and unsettling mysteries in the history of spaceflight. The first whispers of something amiss began in the late 1970s and early 1980s, not with a bang, but with a series of nagging inconsistencies. Engineers at NASA's Jet Propulsion Laboratory, tasked with precisely tracking the Pioneer's trajectories, noticed that both spacecraft were slowing down more than expected. We're talking about an incredibly tiny force here, a deceleration of about 8 billionths of a centimeter per second squared. To put that in perspective, it's like a car slowing down by roughly 1 millimeter every 10,000 years. Yet, for spacecraft traveling at tens of thousands of miles per hour over interstellar distances, these minute discrepancies accumulate, leading to significant deviations over time. The problem wasn't intermittent, it was persistent, constant, and applied to both Pioneer 10 and Pioneer 11. This immediately raised eyebrows. If it were a random malfunction, it would be highly unlikely to affect two independent spacecraft in the exact same consistent way. This suggested something fundamental was at play. The standard models of gravity, solar radiation pressure, and the intricate orbital mechanics of the solar system could not account for this slowdown. Every single known force was being calculated, recalculated, and checked against the observed data, and every single time, there was this missing piece, this unaccounted for deceleration back towards the Sun. The puzzle deepened. Was it a subtle navigational error? No. The tracking methods were robust, using the Doppler effect from radio signals with extreme precision. Was it an onboard anomaly? Perhaps a tiny, persistent leak of propellant that subtly pushed the spacecraft back. Engineers spent years poring over telemetry data, searching for any telltale signs. They analyzed temperature fluctuations, power consumption, and the health of every subsystem. No leaks were detected, and even a hypothesized leak couldn't explain the consistent directionality and magnitude of the force. What about the faint, ambient pressure of the solar wind, or even micrometeoroid impacts? Again, calculations showed these effects were orders of magnitude too small to explain the observed anomaly. The deeper they dug, the more conventional explanations crumbled, leaving only a void. And into that void, strange theories began to creep. Had we fundamentally misunderstood gravity itself? Was there a new, unknown force at work in the outer solar system? Perhaps dark matter was interacting with the pioneers in an unforeseen way. Or was it something far more terrestrial, a mundane oversight that had been missed by everyone? The stakes grew higher. If the current understanding of physics was flawed at the edges of our solar system, what other cosmic truths might be unraveling? As the years turned into decades, the Pioneer Anomaly became a scientific legend, a siren call for physicists eager to challenge existing paradigms. The mystery lingered, a testament to the persistent nature of scientific inquiry. Many leading physicists proposed radical new theories. One popular hypothesis involved modifications to gravity itself, suggesting that Einstein's theory of general relativity might break down at extremely low accelerations, something known as modified Newtonian dynamics, or MOND. Another explored the possibility of a new, unknown fundamental force acting on distant objects in space. Dark energy, the mysterious force accelerating the expansion of the universe, was briefly entertained as a potential contributing factor, although quickly dismissed due to scale and direction inconsistencies. Some even posited an interaction with subtle dimensions or unknown particles. The sheer range of exotic theories underscored the depth of the enigma and the desperation to find an answer. Yet, despite these tantalizing possibilities, the most likely solution often hides in plain sight, disguised as something mundane. Enter the thermal effect. During their long journeys, the Pioneer spacecraft generated heat from their onboard power sources, specifically radioisotope thermoelectric generators, RTGs, which use plutonium to produce electricity. This heat radiated away from the spacecraft, predominantly from the forward-facing, unshielded sections of the main antenna. And crucially, according to Newton's third law of motion, for every action, there is an equal and opposite reaction. As heat photons are emitted, they exert a tiny, almost immeasurable push in the opposite direction. For a long time, precise modeling of this thermal recoil was incredibly difficult due to the complex geometry of the spacecraft and the varying temperatures of different components. It wasn't a simple matter of calculating heat loss. It was about understanding how that heat was distributed and radiated across the entire structure. The spacecraft themselves acted as tiny, inefficient thrusters, constantly pushing themselves forward with their escaping heat. Finally, after years of meticulous analysis, fueled by a grant from NASA and utilizing newly digitized historical data, a scientific team led by Slava Turishev at JPL embarked on a painstaking mission to model the thermal recoil with unprecedented accuracy. They painstakingly reconstructed the thermal environment of the aging probes, analyzing decades of engineering diagrams and telemetry data. The effort was immense, a digital archaeological dig through technological history to understand the subtle nuances of heat physics on distant machines. What they discovered next changed everything. The heat radiation from the RTGs and other components, when modeled accurately and comprehensively, perfectly explained the observed anomalous deceleration. The tiny, persistent push of escaping heat, constantly acting in a direction that pushed the spacecraft slightly towards the Sun, was precisely the force needed to account for the Pioneer Anomaly. The mystery, which had captivated and frustrated scientists for decades, was finally, decisively, solved. So the legendary Pioneer Anomaly, the riddle that hinted at new physics and cosmic secrets, ultimately yielded to the persistent power of scientific inquiry and a deceptively simple explanation: heat. This wasn't a failure of physics. It was a triumph of engineering and meticulous data analysis. It showed us that even our most fundamental laws can be obscured by subtle, mundane effects if we don't look closely enough. While the solution wasn't a headline-grabbing discovery of a new force, its journey was profound. It challenged scientists to scrutinize every assumption, to reevaluate every known physical principle, and to push the boundaries of computational modeling. The Pioneer Anomaly served as a powerful reminder that the universe, even in its most distant and seemingly empty corners, is filled with intricate details that can confound even the most brilliant minds. It taught us that sometimes the greatest mysteries are not solved by inventing new physics, but by understanding the old physics with greater precision. To this day, the legacy of the Pioneer Anomaly continues to inspire scientists to look deeper, to question harder, and to never assume that our understanding of the cosmos is complete. If you want more mysteries like this, the next video explores the perplexing "wow" signal and whether we truly heard an alien broadcast.